Welcome back to the meanwhile 6th video about the details of the A1335 precision Hall effect angle sensor. In the last video we did some noise measurements of the angle output at different output rate settings. I also gave you an overview about what digital signal processing that thing is actually capable of. I think I have it's still laying here. Yeah, that was this one. Anyway, card here, link in the description. Today I want to extend the library again so we can actually set some pre-linearization options. That would be first the pre-linearization rotation, so we can tell the thing are we counting the angle clockwise or counterclockwise? And the second one would be the pre-linearization offset. So telling the thing actually where is our zero position. I mean, we have in our setup here that little detent here, so we have a very well defined zero position, and that should be 0 in our angle readings. Anyway, enjoy! So, the pre-linearization rotation option. That comes actually, that step in the digital signal processing after we already done our angle averaging. We had a look at that in the video before last. I think it was part 4. Card here, link in the description. And after the optional IIR filter, which I haven't talked about yet. And of course there's also that little block here coming before that, that's the angle compensation. But I told you in the last video that's really just used in conjunction with a short stroke mode. We activate the pre-linearization rotation with a single bit flag here somewhere called LR, linearization rotation, I guess. You'll find that LR flag at an extended address within the SRAM as well as within the EEPROM. Of course, we can't really write to the EEPROM. I explained why in previous videos. So we'll go for some SRAM address in that case. Please note that you can write to the SRAM while the chip is in run mode. However, you need to unlock it first by transmitting the key code to it. To be more specific, you find that LR flag at the extended SRAM address hexadecimal 06. And the most significant 16 bits at that address are called ALC-EMP. It's never explicitly stated anywhere in the documentation, at least I didn't find it, but I guess that means algorithm enable. Further down in the programming reference, you find all these flags explained in detail. And for our LR flag, so the pre-linearization rotation direction, it states if the bit is 0, then we have an increase of the angle with a counterclockwise rotation, and if we set that bit to 1, we have an increase of the angle with a clockwise rotation. Please note that is, as the name stated, applied prior to linearization, and we should also look for the RO flag. And this is initialized by the EEPROM field LR, which we can't write, at least not for now. The RO, or rotation direction flag, that was mentioned there is exactly the same, but it's applied after linearization. Otherwise, yeah, the settings are the same, so 0 for an increase with a counterclockwise rotation and 1 for an increase in angle with a clockwise rotation. And it's initialized by the EEPROM field RO. There is another flag here which we will use in this video, and that's SB, the segmented linearization bypass. That's a special override that applies the segmented linearization offset value, which we will also set in this video, but without actually performing the linearization. By default, that's 0, so linearization is performed, but you can set that to 1 to prevent the actual linearization to be performed. Please note SL must be set to 1. That's the flag we have a look at next. And that's initialized by the EEPROM field SB. Who would have thought? Okay, final flag we need today, SL, the segmented linearization. And that enables segmented linearization. There's also something called harmonic linearization, but we will talk about the difference in the next video when we do actually linearize our data. Anyway, 0 disables the segmented linearization and 1 enables the segmented linearization. And funnily enough, there is no mention here of an EEPROM field to initialize that flag. So, these are the 3 flags we actually need within the algorithm enable 16-bit word here, the most significant 2 bytes within the SRAM address 06. We have our SB, the segmented linearization bypass. We have the SL, which was the segmented linearization, and we have the LR, which is the pre-linearization rotation direction. Please note, within this 32-bit word, there's also a 0 offset, but that's not the offset you're looking for. However, we can only, using the I2C interface, write the whole 32 bits here at once or read the 32 bits here at once. So this will bite us in the behind at some point if we just want to write one or the other flag here without destroying or overwriting the 0 offset. So how can we actually write only certain bits in a 32-bit word at an extended address? In the private section of my class, I have a new method, write extended address, that's basically the same like my old write extended address, but it has an additional parameter here, extended data bit mask. And in that bit mask, we can specify which bits we actually want to write, and the other bits are preserved within the register. How does that work? Well, we first perform an initial read at that extended address, and then we do a little bit of bit banging, and then we write the whole 32-bit back. The implementation of that function in the CPP file is almost trivial. So first we read the extended address we want to write to, and we store the data, the whole 32 bits we retrieve here in a local variable. And then we do a conventional write extended address to that extended address. And the 32 bits of data we write to that extended address consist of, well, the previous data binary ended with the binary NOT of our extended data bit mask. So all the bits we don't want to write will be preserved that way. And we binary all that with the actual extended data we want to write, binary ended with our extended data bit mask. That's it. Back in the header file, in the public part of my class definition, we find also a new enum algorithm. That's also an unscoped enum, so you can use bit operations on that one. And this enum contains all the bits from that algorithm enable 2 most significant bytes at that SRAM address. It also contains an algorithm bits value, which is not a single bit, but actually a bit mask of all valid algorithm bits. And you'll find here, amongst other things, the segmented linearization bit. Yeah, switch it on. We talked about that. And the algorithm segmented linearization bypass bit, as well as the algorithm pre-linearization rotation clockwise bit. We also have a new public method here, algorithm, to set actually the algorithm bits within our A1335's SRAM. And of course, if that fails, the function returns false, and we used a last library error to retrieve the fault condition. Anyway, it gets as an argument the bits you want to set or reset, but it gets also as an optional argument here a bit mask, which is by default all algorithm bits. Remember, we defined that bit mask in that enum. But you can use that bit mask to actually set only single bits within that 2 bytes in the SRAM containing all the flags. And here's the implementation of that function in the CPP file. So we just do a write extended address with 3 arguments, yeah, the new one we just implemented, and it gets as an argument, of course, the extended RAM algorithm enable and 0 offset address. And as data, we want to write our bits, yeah, binary ended with the bit mask, so only the bits we really want to set or reset. And just as a failsafe, I also binary end that with the valid algorithm bits. And we turn that into a 32-bit unsigned integer, because that's what we are writing with write extended address. And we shift the whole thing 16-bit to the left to the 2 most significant bytes. And as the third parameter, we pass here the bit mask of the bits we want to write, actually to write. And of course, we have to turn that 2 into a 32-bit unsigned integer and also shift it 16 bits to the left to the 2 most significant bytes. I told you in the intro that we also want to set the pre-linearization offset here. And I hinted at the fact that's not the 0 offset here at our SRAM address hexadecimal 06, where we find our algorithm enable flags. It's actually located further down in the SRAM at hexadecimal 13, and it's called seglin offset. It occupies the most significant 16 bits at that address. Yeah, the least significant 16 bits are again used for something else, but we already have a solution for that with our new write extended address method. Anyways, the value in that field is an unsigned 16-bit integer, and it's converted as n times 360 over 65536. That's of course 2 to the power of 16 degrees. I've actually added 2 public functions to my class here for setting the segmented linearization offset. The first one here gets as an argument the unsigned 16-bit value in 360 over 65536 degrees. The second one, because I really don't want to fiddle with the stuff here, gets as an argument a float. And the range of that float is, of course, between 0 and less than 360 degrees. Both functions can, of course, fail, and then they return false, and you use last library error to retrieve the fault condition. And here's the implementation of these 2 functions in the CPP file. So the one with the unsigned integer argument is really trivial. We just do a write extended address using that new write extended address function, where we can actually pass of write mask here, and the write mask obviously contains only the 16 most significant bits. And then we take our 16-bit offset here as the actual data we want to write to the address, turn that into a 32-bit unsigned integer and shift it 16 bits to the left into the 2 most significant bytes. I also have here defined, like for the other function, a constant, a private constant in my class, extended RAM segment lin offset and cof15. That was the other value that resides at that address 13 address. The second function with a float as an argument is a little bit more complicated. First, we check here if our offset is smaller than 0 or greater equal 360 degrees. If that's the case, we throw a brand new library error, parameter out of range. Remember, that's defined in a public enum in my class definition, and we return false. If our argument is within the range, so between 0 and not quite 360, we scale our offset here by that factor 65536 divided by 360. Yeah, the other way around here, because we want to go from the degrees to the integer value. Next, we check if our scaled offset, we are still here using float values, is greater or equal 65535.5, because that would round to 65536, and that would be an overflow in our integer, in our 16-bit unsigned integer. If that's the case, we correct that down to 65535.5, otherwise we just keep the value. And then we call our segmented linearization offset function with the integer argument, and we just round our scaled offset to the nearest integer. That's it. Now for a sketch to test the whole shebang. But before that, I have to admit I showed you some buggy code. So here in my enum algorithm, I got the positions of some bits or of most of the bits wrong, and I corrected that. As always, you can download the code from my Google Drive. So yeah, let's continue with the sketch. In the sketch, I have some new constants. So I have here a A1335 left segmented linearization offset, currently set to 0. I have the same for my right chip, also currently set to 0. Then I have 2 bit flags here, A1335 left, pre-linearization rotation counterclockwise. That's also set to 0, and the same for my right chip. Then I have a bit mask, algorithm bit mask. Yeah, you remember that bit mask argument for the algorithm function, where I define all my bits that I actually want to set in the algorithm thing. So just the segmented linear bypass, the segmented linearization enable, and the pre-linearization rotation counterclockwise. That's of course just the bit mask. I have also here the bits defined, and this currently contains only the segmented linearization bypass and the segmented linearization enable. I don't have here the pre-linearization rotation clockwise, because that will be mixed in with a binary OR later on from these constants here. The rest of the sketch is basically unchanged in the setup until we are after our, going back into run mode, where we also have to clear that error. I thinned that out a little bit, and I'm just doing now the absolute necessary to clear that error that we were no longer in run mode. And then I have here a lot of statements which are currently just commented out. And these are, of course, my algorithm statements for my left and right chip and my segmented linearization offset statements for left and right, which gets in this case here the segmented linearization offset for the left chip and for the right chip. And here we pass our algorithm bits ORed with the A1335 left pre-linearization rotation clockwise bit and the A1335 right pre-linearization rotation clockwise. And of course the bit mask we just defined. In the loop, I'm now showing just every 250 milliseconds my left and right angle reading here. That's it. So let's have a look at the output. So since we basically didn't change anything to our active code, we have here the same behavior like last time, and I'm just turning here the left sensor to its 0 position. Remember we have that little latch here, and the right sensor to its 0 position. Come on, where are you? There you are. Okay, both are in the 0 position, and everything works as expected. But now let's activate our new code. And for that, I'm just uncommenting that section here with our algorithm and segmented linearization offset statements. Please note that we don't do anything really here. I mean, we don't set that pre-linearization rotation clockwise flag. That's still 0 for left and right. And also the segmented linearization offset is 0 for left and right. So we kind of expect the result to be exactly the same as what we've just saw. And indeed it is. I mean, really nothing changed here. So we're golden. We're golden. Our new code didn't destroy anything. However, there's one thing here I want you to observe. If I turn that wheel here, so the left sensor away from me, I decrease the angle. And that's not really what I want to have. I want to that the angle increases when I turn it away from me. For the right sensor, that's obviously working. That's increasing the angle in that direction until we're back in the 0 position. So let's go back here to the 0 position too and change the clockwise rotation flag for that one. Now I just activated here our algorithm pre-linearization rotation clockwise for my left chip. Let's have a look at the result. Please note I haven't touched here my left axle, so it's still in the 0 position, but please note that the angle reading of the 0 position actually changed when we set that clockwise rotation flag. Also, hopefully note that when I'm now turning the wheel away from me, the angle increases. Okay, so that works. And of course, on the other side, the angle, the 0 position hasn't really changed, and the angle still increases when turning the wheel away from me, back to the 0 position. Now, setting the 0 offset is really simple because we just note these two numbers here, 176.4 and 315.62. And I set these two angles here, the 176.40 and the 315.62, as my segmented linearization offset for my left and right chip. Please note there is no really offset calculation involved here. You just take the output of the chip at the mechanical position you want to be 0, and that's the argument for your segmented linearization offset. Let's see what the chip actually does. And indeed, both my sensors read now 0 at exactly my 0 detent here. So that's wonderful. Same on the other side. Where's my detent? Here it is. So 0 detent, and we are in, within the limitations of my Lego Technic setup at 0. And both now increase the angle reading if I turn the wheels away from me. Nice, huh? So, we're done for today. Just a little outlook. If I turn my right sensor here, and I don't know if you can see the wheel here, exactly 90 degrees, or as exactly as I can set 90 degrees here, I get an angle reading of 180 degrees of very much 180 degrees. So that's fine. Meaning that my magnet is very well aligned to my sensor in the chip. However, when I do that here on the other side, so I go back to 0 and I turn the wheel 180 degrees to the best of my abilities, then I get a reading of 186, which is, well, not quite correct, huh? Yeah, 183. I'm a few degrees off here. Not a few tenths of degrees, but a few degrees. And the reason for that is, of course, that my magnet, I think you can see it from that side almost. Let me zoom in here. Let's brighten that up. Yeah, that my magnet is not very well aligned with my sensor. Yeah. And that's it for today. We successfully, got our rotation direction corrected here in my little setup, and we set a 0 position. So next time we will tackle that alignment error issue here by using the linearization feature of the A1335. Till then, bye.